Alright, so now we're going to be covering all ancestors of a node in a directed acyclic graph. That is Leetcode problem number 2192, which is marked as a medium level problem. So we're given a positive integer n representing the number of nodes of a directed acyclic graph, that is a DAG. The nodes are numbered from 0 to n minus 1, inclusive of n minus 1. You're also given a 2D integer array edges, where edges of I denotes from I to 2I, basically denotes that there's a unidirectional edge from I to 2I in the graph, and we need to return a list answer, where answer of I is the list of ancestors of the ith node sorted in ascending order. A node U is ancestor of another node V if you can reach V via a set of edges from U. Okay, so for this example, let us see what is the, let me just hide the code part and show you this example. So basically the edge list given to us is, there's a node from 0 to 3, then there is 0 to 4 as well, so there's 0 to 4, then there's 1 to 3, right, then there is 2 to 4, so there's 2 to 4, then there's 2 to 7, then there's 3 to 5, right, there's 3 to 5, then there's also 3 to 6, this is 5, and there's 3 to 7 as well, and then we have 4 to 6. So we have to return basically those the ancestors of each node. So let us say we have this answer of I. So at 0th index for node 0, you see there is no ancestor, right? We cannot it has no parents itself, so basically this would be empty. So we return empty for 0. Similarly for 1 and 2, you can see since they have no parents, we have to return empty. So 0, 1, 2, they have no parents, no ancestors, that means no grandparents or anything, so we return empty arrays. Here you can see match it with the output as well, right? But for 3 we see we have 0 and 1, so we add 0 and 1 for 3. Then for 4 we have 0 and 2, so 0 and 2 for 1 for 4. Then for 5 we have 3 as well as 1 as well as 0, so you can see match it here, 0, 1, 3. For 6 we have the nodes, you can see from here, from this graph, 3, 4, 2, 1 and 0. And for 7 finally we have 0, 1, 2, 3. So let me show you for 7. For that we have 0, 1 because it is able to reach it, 0 is also able to reach, and then 2 is also able to reach, so 0, 1, 2, 3, right? So basically this is what we need to return, that is the ancestors. Now this is the explanation, and this is the next example we have. So here also you can see that for 0 we don't have any parents or any other ancestors, so we basically return an empty array for that. Then for 1 we see that we can reach 1 from 0, and that is the only node we can reach it from. Take any other path, you cannot reach 1. For 2 we can reach from 0 as well as 1, right? So we add that 0 and 1. For 3 we can reach from 2, 0 and 1, right, since there are directed edges from each of them. And for 4 we can reach from 3 as well, from 2 as well, from 1 as well, and from 0 as well. Now it's not necessary that there should be a single edge only. Let us say there was no edge between this 2 and 4, but there's also another edge that we can reach indirectly, that is from 2 to 3 and then 3 to 4. So basically we can reach from 2 to 4 indirectly as well, right? So there's no bound given to us that we cannot, we have to maintain a threshold threshold number of edges for it to be equal to valid, right? So there could be any number of edges coming between them, just we need to be able to reach that particular node from our starting node, right? So that's about this explanation of the problem. So now let us get to the solution. So this is the solution that I've posted, and you can see that we will be using topo sort, that is topological sort, or the Kahn's algorithm. So let me share you what is the intuition behind this. So since we are given a directed acyclic graph with n nodes labeled from 0 to n minus 1, for each node we need to return all its ancestors, that is all the nodes that have a directed path leading to it, sorted in increasing order, right? So what we do is we perform a topological sort using Kahn's algorithm, that is BFS, and while processing each node, for each child node we insert the current node as its ancestor, and also insert all the ancestors of the current node into the child's ancestor list, right? This way when we process a node, we ensure that all its ancestors have already been collected. The approach is to build adjacency lists. So we convert the given edges list into an adjacency list and compute the indegrees, so count the indegree of each node. And topological sorting, so we perform BFS, that is initialize the queue with all nodes having indegree equal to 0, then pop the nodes one by one and process their children, add the current node and all its ancestors to the children's ancestor list, then decrease the indegree of the child, and if the child's indegree becomes 0, so push it into the queue, and finally we have to return the sorted ancestor list. So we sort it for each node as required and return it. Now time complexity would be, in order to build the adjacency list, we take O of E because we are traversing for basically if we will go for each edge, right? So in order to build the adjacency list, we go over all the edges, and in the adjacency list that we declare, we push back the each of these, right? So from there's a node, if there's a node from u to v, that means e of 0, u is e of 0 and v is e of 1, right? Because there is a directed edge from u to v, right? So this is e of 0 and this is e of 1. So that is for building the adjacency list O of v. Then topological sort usually takes O of v plus c. For each edge merging ancestor sets O of v times e in worst case, but usually much better due to the set size limits. And finding sorting O v log v. And space complexity is O of v plus c for adjacency and result storage, right? Now let us get to the most important part, that is the code. So get ancestors is the function that we have, and we need to return a vector of int type, and it takes n and the edges matrix as the parameter. So matrix you see is basically the edges from u to v. So as I told you, we're going to be building our adjacency list, and this takes O of e times O of e time, because it traverses all the edges, right? So for all the edges it would be forming the adjacency list. Then we declare our in degree vector, initializing each element with 0, right? Since we're just starting the algorithm, so we have 0 in all the places, so in degree is 0 for the nodes. And then we go over all the edges, and we check if in case there's a directed edge to a node v, then we increase the in degree of the adjacent node, that is the neighbor of u, that is v. Since there's a directed edge, the in degree of this node would increase, so we add that, and this we do for all the nodes. Now we start our topological sort using BFS. So we declare a queue, and for each nodes we firstly push those values into the queue that have in degree value equal to 0, right? So we need to start from those nodes which are actually which don't have any parents, right? So as you saw, we would start our BFS or Kahn's algorithm for topological sort using these nodes, that is the nodes which have in degree equal to 0, that is no incoming edge to them. They may have outgoing edges but no incoming edge. So these are the 3 nodes that we'll push into our queue first, right? In degree equal to 0, and then we maintain a vector of int type toposort to store our topological ordering, and we have answer vector, which is our going to store our final answer. So we check while the queue is not empty, node is equal to q dot front and q dot pop. We're taking out the element from the front of the queue, right? So if we have elements like this, so the element present at the front of the queue, we extract it and pop it out from this queue, right? And we push the node into our toposort, because that would be existing initially in the toposort, and this would be coming in the first area, right? And we traverse basically the adjacency list and go over all the neighbors of this particular node. So from this node, all the neighbors that we can reach, we go over them, and we remove the in degree of this basically node, and we basically subtract it by 1, because now one edge incoming to these 2 nodes, they have reduced. So in degree of the node, the adjacency node, that is in degree of neighbor, decreases by 1, right? So minus 1. And now we add the current node as ancestor. So we check, we find answer of adjacency node, right? And node, so if that is equal to the end, that means that we have not been able to find the neighbor inside our answer vector, then we add it to the add the current node as the ancestor, right? So answer of the neighbor, basically this would be storing the ancestor, right? So answer is storing the ancestor, so this would be pushed in. So for the neighbor, for let us say the neighbor was 1 and its ancestor, that is the starting point, was 0, so it stores it in this format, right? Not an unordered map, but it would store it in this format. This is the index, so this would be at 0th index. So for example, let us say we have a graph 0 to 1, and we have something like this 0 1 2, and we have another ancestor, let us say 3. So they basically answer would be storing at 0th index, we don't have any parents, so that would be missing. For first index we have 0 and 3, so it basically stores 0 and 3. For second index it stores 0, 3 as well as 1, because all of these are its ancestors. And for 3 we have no parents, so again that would be an empty array. Now this is the step for 2 that we'll perform, that add all ancestors of the current node to the child. So the ancestor of 2, or the basically the parent of 2 is 1, but we also need to get the ancestors of 1 as well. So the grandparents of 2 would also be added. Suppose we had another another node, 2 other nodes 5 and 4, who were the parents of 0. So that would be the great great grandparents of 2, right? So these are also ancestors, so we have to add that as well. So for that, this loop is required. So we add all ancestors to the current node to the child. We're going over all the values, right, of that particular node, and we check again that if that is not found here, we add the value or the ancestor to that particular neighboring node as well. So that is given by this one, this syntax. And now if in degree of adjacency node is 0, so we push it because we are decreasing the in degree of each of the adjacency node, or basically the each of those neighboring nodes. So if it comes out to be 0, we're pushing it into the queue again, right? And finally we sort our answer because we need it in ascending order, and we finally return the answer. So that's about the problem.